I would like to give you an update on the latest best practices for vehicle external aerodynamics. So I'm going to start with a couple of general information, talking about the simulation domain. Meshing is an important aspect, setting up and steady and an unsteady aerodynamics simulation, talking about scalability, post-processing, the adjoint solver, and last but not least, some troubleshooting. So, general information. As you all know, Star-CCM Plus is a finite volume-based Navier-Stokes solver. So you have the possibility to run a steady state simulation or an unsteady simulation. I get this question very often. Do I have to run always transient in order to get good results? What are the pros and cons of a steady state simulation? That's why I wanted to start with this aspect first. So steady state, as you can see here, top on the right-hand side, well, there are a couple of well-known pros. So first of all, it is the quick turnaround time, right? So when you compare it to an unsteady simulation, we're normally talking about a couple of hours compared to a couple of days. So this short runtime makes it really the first choice for design studies. The other important aspect is that steady state simulations have proven to deliver accurate results for delta and trend prediction, even for small design changes. Absolute values is another story. I'm talking about that topic on the next slide. But as we all know, steady state approaches, there are also some limitations. So a steady state RAN simulation tends to underpredict the turbulent interaction intensity in the separated shear layer. As a consequence, the lower turbulence level has an impact on the final wake structure, but also on the interactions in the wake. So what we normally see is that due to the lower interactions, the base pressure, that's the pressure behind the vehicle, is normally higher for a steady state simulation. And this higher base pressure results in a lower drag coefficient compared to unsteady runs. So that's what you have to know, and these are known limitations of steady state simulations. So when we're talking about accuracy, the question is also, what is really accuracy, right? And in reality, there are three different levels, categories of accuracy. So when we're starting with, let's say, the easiest one, well, to be honest, it's not always that easy, is basically the prediction of a trend or a ranking. So is your design change better or is it worse? On top of it is the delta prediction. So if you're changing something, how much better is it compared to the baseline? Or is it worse? How much? And the top is really the absolute value prediction. We can see here that for trend rankings, deltas, steady state RANs is absolutely fine. And you can see also the dashed line, even for some cases, steady state RANs is able to predict absolute values. So for example, when you have a sedan where the flow is mainly attached, you have a very small unsteady wake, you can also get very close with steady state methods in terms of absolute values. But as soon as you have an SUV or a truck or something like that, where you have big unsteady wake structures, it definitely makes sense to switch to an unsteady simulation, to DES, LES, in order to predict absolute values. So I think that's an important information. What can you achieve with steady state, and when do you really need an unsteady simulation? Simulation domain. Okay, so as we all know, there are basically two approaches when it comes to a simulation setup for external aerodynamics. So the first one is basically open road, and the other one is the wind tunnel setup. So the open road setup is basically, as you can see here, a big box, right? So the goal is really that you have the boundary conditions far away from the vehicle, so that you have no influence from the boundary conditions on the flow field, on the final result. And this setup is good to predict deltas and rankings. The other story is when you're targeting absolute values. And if that's your goal, it really makes sense to include the most important aspects from the experimental setup in your simulation. So when we look at a wind tunnel, you can see here that we have the nozzle, we have a belt system. Maybe it is single belt, like in the picture here for sports car. Maybe it is 5 belt. We have boundary layer suction. We have maybe a scoop, so boundary layer treatment in general. We have blockage ratio, collector influence, and so on. So there are really many aspects to consider. So when you're really targeting absolute values, it's maybe not just recommended to use an unsteady method, but also to carefully consider the experimental boundary conditions. So in this picture, you can just see here an example case where we have a wind tunnel, the test section, the nozzle dimensions. You can see here the belt is modeled with tangential velocity, and we have pretty good experience in modeling the boundary layer treatment. So as I said, suction, tangential blowing, or a scoop with just a slip wall boundary condition. Because at the end of the day, the goal of all these devices is to remove the boundary layer from the ground. And that can be achieved with a simple slip wall boundary condition. Okay, so let's start with the simulation setup. Let's start with the meshing. Yeah, boundary layer, turbulent boundary layer theory, very important aspect, of course. I'm not going into the details here because you can find everything in a good book and it's much better explained than I can do it. But I want to mention here that we have 3 areas, let's say. We have the viscous sublayer close to the wall, we have the buffer layer and the log-lar region, and we have to create our mesh so that it fits to these different areas of the boundary layer. So there is a low Y plus mesh approach. So as you can see on the right-hand side picture, we are putting the first cell centroid within the viscous sublayer. We are adding a sufficient number of boundary layers in order to resolve the velocity gradient. The other approach is the high Y plus approach. So here we are working with wall functions. You can see here the viscous sublayer is modeled with wall functions, and we have a coarser mesh. So the nice thing is in Star-CCM Plus, you can combine these 2 different approaches, but I'm going to talk about them in a couple of minutes. So when it comes to Star-CCM Plus, let me try to highlight that for you. First thing is what you can see in the picture right-hand side is when you click on the prism layer measure, you have here the expert properties of the model is to switch the distribution mode to wall thickness. So with this parameter or with this option, you can specify the prism layer thickness next to the wall. There are a couple of other relevant parameters. So for example, minimum thickness percentage or layer reduction percentage. Well, at the end of the day, the goal is really to have at least 1 prism layer cell everywhere in order to help the solver. So that's the goal. So for example, changing the minimum thickness to only 1, so that means 1% of the global prism layer's thickness is the minimum thickness. You're really, let's say, achieving a prism layer cell even in the smallest gaps. So that's the goal at the end of the day. Yeah, so you can see here 2 examples of a high Y plus mesh on the top, low Y plus mesh at the bottom. Well, at the end of the day, the goal is to avoid also the buffer layer between 3 and 30. I know it's not always possible, but for the important surfaces like the exterior surfaces of a vehicle, you should really make sure that you are within a suitable range for the Y plus value. So in general, I recommend to create a low Y plus mesh on the exterior surface of the vehicle. So that's what you can see here at the bottom. And for the remaining surfaces, so for example, for the engine compartment, so definitely for the engine compartment, high Y plus, 1 prism layer is absolutely enough. We don't have to resolve a boundary layer there. The underbody, it depends on the type of vehicle you're simulating. When you have an electric car, maybe you have a very smooth underbody, maybe a diffuser that is working. Then I also recommend to create a low Y plus mesh there. But if you have, let's say, a traditional car with exhaust system, suspension, and so on, high Y plus 1 or max 2 prism layers is absolutely fine. As I said, Star-CCM Plus is able to handle a mix between these 2 approaches. So at the beginning, the distance of the cell next to the wall is calculated, and Star-CCM Plus automatically switches between low Y plus and high Y plus approach. But again, it is always recommended to use an all Y plus wall treatment. So don't select a low Y plus wall treatment or high Y plus wall treatment. Always select all Y plus wall treatment. Yeah, a couple of settings here, number of prism layers. In the past, I saw cases with, I don't know, 30 prism layers or something like that. You don't need that. It's just adding a lot of cells. 8 to 12, 8 maybe the lower end, 10 to 12 is absolutely fine. This is just to give you an idea, 8 millimeter in total thickness, 0.03, 0.05 millimeters as thickness next to the wall. So that guarantees a Y plus value in the range between 1 and 2. And that's the goal at the end of the day. Okay, we talked about the prism layers. Next topic is the volume mesh. So as you can see here, top left-hand side, in the past, it's very convenient to just create a block in order to define a volumetric control. But as you can see here, that you are also wasting a lot of cells. For example, above the bonnet. I mean, literally nothing is going on there. And I saw cases where there were easily 2, 3, 4 million cells really wasted in this area. And that's not what we want, because at the end of the day, we want quick turnaround time. In order to achieve that, we implemented almost 2 years ago a very nice feature, and that's the so-called offset feature. So it's a mesh operation, as you can see here. And all what you have to do is basically just select the car, the wheels, and the vehicle components and just create an offset. You don't need a watertight surface. It literally takes everything and you just create an offset. So what I normally do is what you can see on the left-hand side. I just create 2 offsets, 20 centimeters and 50 centimeters, and you can create a sort of body-fitted mesh. So you can see here above the bonnet, very nicely meshed. Of course, you can control the transition and so on, the speed of transition. But you can see here, we are not wasting cells. So that's actually pretty nice, and I highly recommend to use that. Well, let's have a look at the wake of a car. We also need some refinement here. So normally I'm doing that with some blocks, what you can see here basically, and another one. So it's a rule of thumb that, for example, 50% of the vehicle length, that's the length of the refinement in the wake of the car. So 50% of the base size. So the global base size, I'm actually using 24 millimeters or 32 millimeters. And that results in a mesh size in this area of, let's say, 12 or 16 millimeters. Yes, and we need some additional controls also for the tire wakes and for the mirror wakes and so on. But just to give you an idea here, so that's how volume mesh looks like in Star-CCM Plus based on the recommended settings. Yeah, as you can see here, by the way, we are using the trimmed cell mesher for external aerodynamics. Maybe a few quick comments about poly versus trimmed. As you may know, we have released our new parallel poly mesher in version 2020.1. And I also did some quick tests comparing the poly mesher and the trimmed mesher. And I have to say the results of the new poly mesher are really great. So to give you an idea, for an industrial case of 80 to 90 million cells, meshing on 500 cores, the trimmer, it's done in 5 minutes. The poly meshes in the range of 20 to 25 minutes. It's still a bit slower, but the performance is really, really good. And the poly mesher has a big advantage. The cell quality at the end of the day is better compared to the trimmer. So why do we still recommend the trimmed cell mesher for aerodynamics? Well, first of all, the trimmer is still a bit faster, but that's not the main advantage. The memory consumption is a bit lower, but the most important aspect is that for aerodynamics, we have directed flow, of course, aligned with the mesh. So that's very important. But the most important one is again that Star-CCM Plus is a phase-based solver. So a standard hex cell with 6 phases, a poly cell is maybe 13 or 15 phases. At the end of the day, the solving time is smaller with the trimmed cell mesher. That's why the trimmer is still the first choice, at least for the time being. Okay, enough said about the poly mesher. Let's go back to the mesh settings here. As you can see, 100% of the base size. The trim cell mesher, we always have the volume change 1 to 8. So that's why we have always to double the mesh size or multiply it by 0.5. So we have for 100%, we have 50%, 25%, 12.5%, and so on. That's important. Another important aspect is volume change. So you have to make sure that you have everywhere in the domain a smooth volume change between the different cells. As you can see here at the ground, I recommend to create a couple of prism layers there. So that's especially important below the car, but also when you are far away from the car, you have to make sure that you have a smooth transition. So that please don't create a very thin prism layer cell and the first volume cell is dramatically big. That's not recommended. That's not good for the solver. So that's why I recommend to create an anisotropic refinement close to the ground. You can find the settings here and you can see that we have a nice transition in terms of volume change. So another important aspect for the meshing is the tire ground contact. And that's really an important aspect. Basically, you have two approaches. You can see on the left-hand side that I would say that's maybe the traditional one. We just take the tire, intersect it with the ground. There are, of course, some critical areas. So here you have this sharp angles, right? And it's sometimes a challenge to keep the prism layers there. As I described previously with the expert properties of the prism layer mesher, you're able to also keep some of the prism layers in this sharp corners. The other approach is to create a small socket. And when I'm talking about a small socket, I'm not talking about, I don't know, 8 or 10 millimeter socket or something like that. I'm really talking about 1.5, maybe 2 millimeter height. That's important. Otherwise, you're really altering the flow field a lot. The advantages are pretty obvious, I would say. Better mesh quality, better stability at the end of the day. As you can see here, we're able to keep the prism layers, so it looks better, right? I have to add that what you can see here is a tire with longitudinal grooves, that the impact of a socket on the aerodynamics of a tire with longitudinal grooves is not that big compared to a slick tire. So when you have a slick tire and you're adding a socket, of course the flow field is changed, is modified. So that's what you always have to keep in mind. But I'm talking about tires in a couple of slides and a couple of minutes. So the last meshing aspect I would like to talk about is the cooling package. As you can see here, we have a couple of heat exchangers. So if it is a radiator, condenser, and so on, we have a couple of recommendations here as well. So the first one is that you should create a prism layer cell on the fluid side of things, on the fluid interface. As always, and that's true for all interfaces with Star-CCM Plus, I would say, you should make sure that the mesh size is roughly the same on both sides of the interface. For the heat exchanger cores, I recommend the directed mesher. You should create 6 to 8 layers in the flow direction. What else do we have? Yes, for the MRF region, so for example, for the tires, but also for the fans, we recommend to use the poly mesher. So let's start with steady-state aerodynamics. And the first aspect here is tire modeling. So as you can see here, for steady-state aerodynamics, for the MRF approach, I recommend to extract the fluid volume between the rim spokes. That's what you can see here. You can see also what I already said for the cooling package, same mesh size on both sides of the interface. We recommend to create a prism layer on each side of the interface and poly cells for the MRF region. Poly cells, as I said, better mesh quality. The flow here is more anisotropic. That's why we recommend the poly mesher here. So I know that it is sometimes a challenge to extract the fluid volume between the rim spokes, but it is really important to, let's say, follow some rules, some guidelines when you're using the MRF approach. So originally the MRF approach was designed for axial flows. So the flow direction should be parallel to the rotation axis. So you should avoid any tangential inflow. And that's what we are doing when we are extracting the fluid volume between the rim spokes. So let's analyze that. Let's see how big the impact really is. So as I said, I fully understand it's sometimes a challenge to extract the fluid volume between the rim spokes. So as a compromise, you can also create, let's say, a cylinder, but you have to move the cylinder very close to the rim. So in this case, the tire wall is basically shielding the MRF region. And in this case, we can avoid the tangential inflow into the MRF region. So that's what you can see on the left-hand side. So the MRF volume, even modeled as a cylinder, moved very close to the rim. On the right-hand side is the other extreme, I would say. The MRF region really extended into the main volume, into the main airflow. So let's have a look at the results for these two cases. And you can see on the left-hand side, again, the small MRF volume, the small MRF region moved towards the rim, and on the right-hand side, the extended MRF region. And you can clearly see that the MRF region is changing the flow field. And when we have a closer look, you can see it here on the bottom right. We can clearly see the MRF interface in the flow field. And that's not what we want. So we can see here some unphysical results. And we can also see that it obviously has an impact on the integral values. So it is an increase of 7 drag counts only due to numerics. And that's not what we want. So that's, again, why we recommend to be very careful in placing the MRF volume. Make sure that you don't have a lot of tangential inflow into the MRF region. So the final slide about tires. Tires are extremely important, as I said at the beginning. So the tire wake is traveling downstream. It's impinging on underbody components. So it's really critical. So in the past, our customers, and I'm not an exception here, we just intersected the tire with the ground. That's what you can see here, top right. But that's actually wrong, and we are introducing a lot of errors here. So what you should do is you should really make sure that you're keeping the longitudinal grooves at the ground. They are extremely important because they enable a pressure decrease between the front and the back of the contact patch. And that's extremely important for the aerodynamics, for the wake structures of the tire. So as you can see here, it's the same geometry, but I just created a subtract in Star-CCM Plus to make that happen. You can also do that. It's really important that you respect these rules. I know it's challenging to have a deformed tire shape. It requires scanning the deformed tire. Then it needs some manual preparation. I know it's not available for everybody. If you have it, it's very nice. You can include it in the simulations, obviously. So these are the recommendations for a tire with longitudinal grooves. As I said, apply tangential velocity for the tire surfaces. Make sure that you keep the longitudinal grooves at the ground. When you have a fully treaded tire, the procedure is basically the same. Well, tangential velocity is actually not correct for lateral grooves. There are a couple of nice studies from Chalmers University in collaboration with Volvo. So for these grooves, the MRF approach is recommended. Okay, so we talked about tires. Quickly, a couple of slides about turbulence modeling. I won't go into the details here. I'm really not an expert. I can't explain all the different equations, but I think that's not needed. So for me, the standard model, I would say, for steady state run is the Omega SST model with 2 small modifications. So the A1 coefficient and the reliability coefficient, also published by my colleagues here. Feel free to have a look. It's available on the internet. Well, the Omega SST, with these 2 modifications, we have very good convergence behavior. So we have an excellent prediction for drag, but also for lift. So I would say that's my standard model. We have another interesting model, and that's the so-called lag EV capsulum, EV elliptic blending. So that's basically a 3-equation eddy viscosity model, closer to a Reynolds stress model. And for example, when you have a car or vehicle where vertices are traveling downstream, so the EV lag can be a very interesting model for your applications. And again, you can find more information in the literature about this model. We worked a lot on this model and also improving the stability and also the convergence behavior, in some cases even better than the K-omega SST. So we definitely encourage you, give it a try and let us know how it works. But I would say that really standard one, K-omega SST, and you should be fine. So in terms of turbulence modeling, well, that's a point many people forget from time to time. So boundary conditions, to be honest, I'm not an exception here. So when you go to the physics continua, you also have initial conditions for turbulence modeling here. So for example, to be totally honest, velocity scale, default is 1 meter per second, intensity 1%, turbulent viscosity ratio 10. And to be totally honest, they are not related to any, let's say, experiment, academic case, a flat plate or something like that. These are just good looking numbers. That's how it is. 1, 10, just good looking numbers. So when you have parameters from the experiment, for example, turbulent intensity, so modern wind tunnels, they are below 1%. Please add this information also under initial conditions. For the velocity scale, I'm putting in the inlet velocity normally. And the same is true for the inlet conditions. So for the tunnel inlet, for example, when this information are available, please add them because it helps the turbulence model a lot. Another settings for the cooling package, as you know, we are modeling the heat exchanger cores with porous media in Star-CCM Plus. So we're modeling the pressure drop here. So we have the inertial resistance. So that's multiplied with the velocity squared. So here I recommend to put the cross-flow component to 0. As I said, it's multiplied with velocity squared. So very high values can create some instabilities. And for the viscous resistance, I recommend to increase the cross-flow component by 1 or 2 orders of magnitude, and that should be perfectly fine. So we talked about tire modeling, turbulence modeling. We talked about the cooling package. Let's talk about the solver. And there were a couple of changes in version 2020.1, and I would like to talk about that here in greater detail. So for steady-state aerodynamics, we recommend to use the coupled solver. There are a couple of advantages. So it is more stable, it converges faster, you have more capabilities, features in order to initialize the simulation, and so on. There are 2 parameters. There is the CFL control and the explicit relaxation control. And the coupled solver tries to find a good balance between these 2 parameters. To be totally honest, in the past, it was a bit difficult, challenging to use the coupled solver. It was not running out of the box, and we got this feedback from our customers. That's why still many people prefer the segregated solver, because normally it runs out of the box and the coupled solver doesn't do that. So that's why we said, okay, we have to reorganize it. We have to make it more usable for our customers. That was priority number 1. So that means we cleaned everything up. So we removed parameters nobody was using. And we're ending up now with basically 2 options. So CFL control method and explicit relaxation method. And point number 2 is that we added an additional option for the CFL control. So you have the traditional ones, the old ones, let's say constant linear ramp and expert driver, but we also have a new one. and that's called automatic CFL. So when we look at expert driver, so it's still available. You have to specify the target CFL value and so on. And when we compare it to automatic CFL, you can see here that we have an initial CFL and we have a minimum CFL and also a maximum. And the maximum is 100K. But you don't have to touch these parameters because automatic CFL is, as the name suggests, automatically calculating the best CFL number. There is just one parameter you can touch, not needed, but you can give it a try, and that's the target AMG cycles. So the default value is 4. I normally increase it to 6 to 8. And that's basically the aggressiveness of the ramping. And then that's all what you have to do, and then you are good to go. So a couple of settings you can find in the best practice document here is related to the expert driver. So what is special? So well, we are changing the inviscid flux options to ROE, FDS, no blending, basically adding a bit more dissipation to make the simulation more stable. And we are also changing the normalized flat side curvature factor to a very small value in order to force green Gauss in the prism layers. So that's basically what we did, all what we did. As I said, the expert driver requires a target CFL number. That's what you can see here. Yeah, as you can see, 100 to 150. What is the best one? Well, it depends on your case, but you don't have to define that with automatic CFL, and that's the nice aspect. Again, you can see it here, basically a study for an industrial case. You can see here with a CFL number of 50. Well, maybe you need 4,000 iterations, maybe a bit more. When you specify or define 150, maybe just 1,500 iterations, and it's much faster. So that's really up to the user. But again, it's no longer the case with automatic CFL. And that's what you can see here. So on the left-hand side, you can see, let's say, the CFL history for the automatic CFL option. And on the right-hand side, you can see the CFL history for the expert driver. So when we look at the right-hand side, we can see that the expert driver is doing what it's supposed to do. So it's really targeting a CFL number of 100, and that's it. When we look on the left-hand side, we can see that the 100 is more or less the lower bound of the CFL range. And the max bound is maybe around 200. And we're somewhere in between, right, as I mean. But you as a customer, as a user, you don't have to take care about that. You just select automatic CFL and hit the run button. So you don't have to think about, okay, what is a good CFL number for this vehicle or for this one? It's done automatically by the automatic CFL option, and that's really a nice. Again, when we look at the table of settings for the automatic CFL, everything is the same basically. As I said, there are a couple of differences, of course, related to automatic CFL. So the target AMG cycle number default is 4. You can try 6 or maybe 8. I think 8 is really the upper limit here. And that's it basically. So by the way, we changed also the pre-sweeps default in Star-CCM Plus for 2020.1. So you don't have to take care about that one. And that's it basically. So that's the new automatic CFL. At the end of the day, both approaches should give the same result. Of course, that's important. We did many tests here. You can see automatic CFL is a bit faster in terms of convergence rate. You can see at the y-axis, the resolution is 1 drag count. Again, important is the same result, but convergence is faster. And again, you don't have to be a super expert with many years of experience of tuning all the different parameters in the expert driver. You just select automatic CFL, maybe increasing the target AMG cycles a bit, but then you're good to go. Okay, so we talked about steady state. As I said, MRF for the tires and tangential velocity, and the coupled solver as a solver. Omega SST is a turbulence model, and that's it basically. Let's have a look at unsteady aerodynamics and what's different. So first of all, some of you would like to include RBM, rigid body motion, in the simulation. So you would like to have a real mesh motion in the simulation, and that's what you can see here. So the yellow volume is the RBM region, and as I already said, for the cooling package, but also for the MRF setup, we have here the same recommendations, the same mesh size on both sides of the interface, one prism layer cell at each side of the interface, and poly cells for the RBM region. That's it, basically. To be totally honest, sliding interfaces at the moment is a bit of a bottleneck in Simcenter Star-CCM Plus, and customers and also we tried some pseudo parallelization by splitting up the interfaces. That's what you can see here, top right hand side. So having a couple of interfaces in order to get some pseudo parallelization. To be totally honest, the results we got were not consistent. So it depends on the case, it depends on the hardware. Then you have to keep in mind that some additional preparation upstream of the process is needed in order to split up the interfaces. During the solving process, it can happen that not every face is not perfectly matching on the interface. So that's why we recommend to create just one interface for each wheel for the time being. I can tell you that improving the performance of sliding interfaces is one of our highest priority development. So our colleagues are already working on that topic, are testing different approaches. Unfortunately, I can't tell you a release date, but again, this is really a high priority topic to speed up sliding interfaces. So the video looks like this. So you're running a steady state simulation first in order to initialize the flow field. Then you're switching to unsteady setup. Basically, all what you have to do is, I prefer to have a second physics continua. Well, then of course with implicit unsteady, we recommend to use a second order temporal discretization. Default is first order, and the recommended turbulence model is SST as underlying RANS model, and the late detached eddy simulation as a DES formulation. Again, the improved delayed detached eddy simulation model is the default option, but we recommend for aerodynamics the DDES variant. We did many cases in the past, and we saw that the DDS model is just more consistent when it comes to delta prediction and rankings between various designs. We know for unsteady aerodynamics, there are a couple of parameters in order to speed up the simulation. So initialization is an important aspect. Number of iterations per time step in combination with a smart choice of relaxation factors. So this of course depends on the mesh quality, how hard you can, let's say, push the solver, time step size, but also the mesh, of course. So there are a couple of parameters at the end of the day. So when we look at the best practices for unsteady aerodynamics, one important aspect is, of course, that we are using the segregated solver for unsteady aerodynamics. A segregated solver iteration is just much faster than a coupled solver iteration. What else is important? Well, time step size. I'm going to talk about time step size on the next slide. As I said, relaxation factors depends on your setup. What else do we have? Physical time. I have another slide about the physical time. Yeah, and the max in iterations. Well, you have to check convergence. Again, it depends on the case. So let's talk about the time step size. And of course, that's a question I get on a regular basis. Which time step size do I have to use in my simulations? Well, you can see a lot of text, but let me try to highlight the most important aspects here. So first of all, when you are running a simulation with RBM, with a sliding interface, we have a rule of thumb that says don't rotate more than one cell per time step. And when you have a normal velocity of 140 kph and let's say a standard tire, you're ending up roughly with a time step size of 2e-4, 2.5 e-4. So in such a case, the do not rotate more than one cell per time step rule of thumb is basically defining the overall time step size. The beauty of Simcenter Star-CCM Plus is that you can also combine different methods. So for example, for the main flow, you can use an unsteady method, so DS. So for example, in order to resolve the unsteady wake of the vehicle, but you can also combine it with, let's say, steady methods in order to model the tire rotation. So this can be, for example, MRF between the rim spokes and tangential velocity. So in such a case, you can also go for a pragmatic approach. I call it pragmatic approach because you can use, for example, a time step size of 1 millisecond, maybe combine that with 10 iterations. And of course, you can get a solution much faster, obviously. So the important thing is to keep in mind, when we are increasing the time step size, we have to pay a price for that, obviously. And the price is that, based on our experience, is that the absolute value for the drag coefficient increases. So imagine that you have two variants and you're analyzing that with a very small time step size. You're increasing the time step size. The absolute values will increase, but the deltas between the two designs, and that's actually the important aspect. So the deltas and the trend prediction is extremely consistent, even with the larger time step size. And that's actually the important aspect, I would say. So at the end of the day, convergence is important. So you should make sure that residuals are dropping. Another aspect you can monitor is that you are monitoring the pressure convergence. It's the hardest parameter to converge. So you can create some point probes, put them into, let's say, challenging regions, detached regions, and monitor over the iterations. And that's important, over the iterations, the convergence of the pressure. Of course, it should flatten out within a time step. So to sum it up, again, RBM is defining more or less the time step size. When you have steady state methods, you can also go in a pragmatic approach by increasing the time step size. How long do I have to run in terms of physical time? Well, that's a pretty simple question because it really depends. It depends on the overall flow characteristics, on the flow physics of the vehicle. So you can roughly say that a sedan with a mainly attached flow, you're in the range of maybe just 2 to 3 seconds. When you're looking at as an SUV, it can take actually maybe 4 or 5 seconds. Again, these are just rough estimates to give you an idea. The message is really, when you have a bigger unsteady wake, you normally need a longer runtime in order to get a statistically converged signal. In order to monitor that, you can create a statistical report in Simcenter Star-CCM Plus with a sliding mean, actually a nice feature. And again, when you have a steady initial solution, it takes some time to wash it out. So I would say normally the first maybe 0.5 or the first second is really needed in order to get, let's say, the steadiness out of the simulation, and then you can start the averaging. A dedicated slide for truck aerodynamics in terms of meshing. Yeah, as I said, it's the same for a car. The really relevant external surfaces are low Y plus mesh on the truck, and everything else is high Y plus. Physical runtime is important, especially for the data averaging. Time step size can be even a bit more aggressive, so 2 milliseconds or maybe even 2.5 milliseconds is fine. Physical time, well, it's much longer compared to a car, so 15 to 20 seconds, and doing the averaging over the last 15 to 20 seconds, over the last 15 seconds, if 20 seconds are available. Okay, let's talk quickly about scalability. I think that's an important aspect. So we are promoting that, but we got, to be honest, a complaint from one of our customers telling us, well, we did scalability testing on up to 3,000 cores, but it's actually not that good. So what's happening here? And you can see here on this plot on the y-axis, the speed up, on the x-axis, the core count, and the red line is the ideal speed up, and the green line is what we reported. So we asked the customer, can we have the case? Can we run it? And we did that. And you can see, well, the customer is right. It's pretty disappointing. And It seems also that this customer and maybe also some of you have a legacy workflow. I know it's not so easy to change a legacy workflow when it is used in a production environment, but maybe some of you are still using region-based meshing and so on. So we definitely encourage you to update to the latest best practices. And one of the best practices is really to streamline your SIM file to make it sleek and smooth. So having a minimum number of boundaries, for example. So when you look at the green line here, we have here 750 boundaries. So I would assume this is just input the geometry, assign paths to regions, and you get for every surface a boundary. But then one of my colleagues, he condensed down the number of boundaries, and you can see here that the overall scalability is much better. Yeah, so it's really, if you have time, try to update your workflows, your templates, and your settings, because you can see here that you're really benefiting from the latest releases and features in Simcenter Star-CCM Plus. Post-processing, that's a quick one. I'm not going into the details here because drag and lift coefficient setup, this should be really straightforward. One comment I would like to make here is the frontal area. Please do not use the frontal area report expression. So don't use a report in a report, because when you are, let's say, plotting the drag, for example, every iteration or every time step, the frontal area report gets somehow re-executed, and this is really harmful for the overall performance and scalability. So you have two options: just put in directly the number, or you create a parameter under tools, and then you're adding here this parameter for the coefficient definition. That's important. Yeah, what else do we have? Accumulated force plots, very nice feature within Simcenter Star-CCM Plus. Just creating a table, basically adding the important relevant parts, and you can see here how the force, let's say, develops over the car. This is at the moment available for steady state, but one of my colleagues, he created a nice article on the Steve portal, how you can do it also for transient simulations. And by the way, we are implementing this feature also in Simcenter Star-CCM Plus Automotive Aerodynamics workflow. So that's the former vSim tool. So this functionality will also be available soon. There are also a couple of other really interesting, good articles on the Steve portal. Please feel free to have a look. At Joint Solver, just a couple of quick notes here. I guess you're aware of this functionality. Again, this is based on the coupled solver, a steady state simulation. So the so-called primal solution is calculated first. And based on this primal solution, the joint solver is executed. And as a result, you can see again on the right-hand side, a fully industrial case with all the details. And you get the following information. Well, a positive surface sensitivity suggests to push the surface inwards in order to reduce the drag. A negative surface sensitivity suggests to pull the surface outwards. We worked a lot on the coupled solver in the last years. We improved a lot the convergence behavior, but also the requirements in terms of primal convergence, and we really made some great progress here. You can also find here a workflow, a recommendation. Well, it looks complex, but it is not complex. I would say start with right preconditioning, use first order a joint, and use as many Krylov vectors as memory permits, and then you're good to go. I gave it a try for many industrial cases, and it works really, really nice. Okay, last but not least, troubleshooting, an important aspect. So the recommended workflow is to use cell quality remediation. Well, when we are importing a super complex geometry, we wrap everything. It can happen that you're ending up with some low quality cells. That's why we use cell quality remediation. It's basically adapting the numerics. So switching to first order, something like that. Remove invalid cells. So this is needed when we have a negative volume cell. As I said, it can happen with these complex geometries. Just remove it and you're good to go. And the other important functionality is split non-contagious. So maybe you have encountered this warning or this error message in the output window, something like AP equals 0 on multi-grid level, AMG coarsening halted, and so on. So in, I don't know, 90 point something percent, it is related to this non-contagious volumes or phases. So the AMG solver doesn't like that. So what I do is go to the region, right-click, split non-contagious. I normally use 1E-12 for the minimum connected phase area, split up the volumes, disable the physics, and you're good to go. The functionality is temporary storage retained. So this option is available for every solver type. So you can activate it. You get a bunch of new field functions. You can monitor the local residuals and so on. Again, keep in mind you have to run an additional iteration in order to fill all the field functions. Monitor the max velocity in the domain. Make sure that you have a good mesh quality, especially in the prism layers. And a final comment about switching from steady to unsteady here. So it can be beneficial in some cases to start with a larger time step size or play around with anodization factors. So most of the time, to be honest, I don't do that. So I switch directly from steady to unsteady with the fine time step size. But maybe with the coarser time step, you can also speed up washing out the steadiness. One final comment here. So if your simulation runs only with first order numerics, there is definitely something wrong in your setup. So it is really highly recommended to review, especially the volume mesh. Most of the time it is related to the volume mesh or maybe to the overall setup or boundary conditions. But again, to be honest, I'm never running cases with first order turbulence or first order convection or something like that. So if that's the case, there is definitely something wrong in your setup. Okay, so that basically concludes my presentation. So I was talking a lot. Sorry for that. I hope you were able to follow up on that. By the way, the document, you can find the document as it is on the Steve portal. So just search for best practice vehicle aerodynamics and you can download the PDF. So we have a couple of minutes left for your questions. So please feel free to add more questions in the chat. So let me see, what do we have here? So, so there's a question regarding the DES pragmatic approach. I'm using 1 millisecond of a time step size. Is this using MRF and tangential velocity? Yes, it is. So we had a very nice presentation from Maserati during our last Simcenter conference in Amsterdam in December last year. And that's exactly what they did. So actually they were putting the car into the wind tunnel. They also modeled the wind tunnel, but they were not using a rigid body motion for the wheels and for the tires. They did DES simulation, but they really used MRF between the rim spokes and tangential velocity for the remaining tire surfaces in order to model the tire rotation. And they were analyzing different rim designs in terms of ranking, in terms of deltas, and they got very, very good results. I have to say they also included a deformed tire shape, so they really put in a lot of effort in this setup. But again, they were running DES with, I think it was 2.5 E-4 seconds as a time step size. So really a small time step size. And they were using MRF with tangential velocity, and they got very good results. But again, the pragmatic approach, 1 millisecond as a time step size, is in combination with MRF and tangential velocity. Yes. So there is another question. Why do we need polymesh in MRF regions? It's a good one. Well, you can also create a trimmed mesh in the MRF regions or in the RBM regions. And the thing is, the polymesher produces a better quality mesh. So for example, the rims where you have many curves and so on, the polymesher is better quality at the end of the day. And as I said, in these areas, you have an anisotropic flow, you have more turbulence going on. the flow is definitely not aligned in these volumes. So that's why we recommend to use the polyhedromeasure. So there is a question, have you recorded this presentation and is it possible to get it? Yes, I think it is available. To be honest, I have to double check with my colleagues, but I'm pretty sure it is recorded, and I think it is also available to watch it afterwards.
Peter, this is Scott Walensky calling, and to answer that question, yes, it is recorded. We will be placing it up on the customer support portal, and once it is up there, it will be available for download. We usually do that within a day or two after the presentation.
Okay, very nice, Scott. Thanks. So there's another question about speeding up the RBM and its interfaces. So the question is, are we talking about a couple of releases maybe, or a bit longer? So as I said, unfortunately, I can't give you really a release date, but I can tell you that we are already testing different approaches, and I would say you can expect something beginning of next year. Again, it's not carved in stone. As you know, something can change, and all of a sudden we find a regression or something like that. But we're already testing something, so I would expect something beginning of next year, or let's say in the releases of 2021. So let me check. Do we have a couple of more questions here? Okay, there is another question about the automatic CFL. So the question is about the target AMG cycles, indicates how aggressive the solver is. Does it mean the higher the number is, the more aggressive the solver is going to be? Yes, that's exactly how it is. So the default value is 4. And when you increase the number, so I tested really up to 10 or something like that, but then it doesn't make sense anymore. So I would say that the sweet spot is somewhere between 4 and 8. So when you put in, for example, 6 or 8, so higher than the default value, it is really more aggressive, and you're basically using more iterations to ramp the CFL number up. So yes, higher number for the target AMG cycles, the solver is more aggressive, and if you have a good setup, you should get a solution faster. So let me see if I have more questions here. So there's another question about why do we still have or recommend a joint solver first order? Because we promoted second order also in the past. Well, the thing is, to be totally honest, it's still more challenging to get second order adjoint converged for full industrial cases. It is possible nowadays. To be honest, I did this for some cases, and for some vehicles, the difference is very, very small. But for other cases, I have to say that the second order solution is noisier than the first order solution. So you doesn't get a benefit at the end of the day, I would say. So that's why I still recommend to use first order adjoint for industrial cases. Let me see, what else do I have? So there's a question about the small and the big MRF sizes. So you gave 7 counts drag between small and big MRF cylinder. How big would be the delta to MRFs between the spokes only? So I guess your question is related having a small cylinder compared to an MRF setup only between the rim spokes. So, well, in an ideal world, when you have no tangential inflow, I would say the difference should be neglectable. Well, at the end of the day, there might be a small difference between these two setups, but I would say it's really neglectable. So the case that I showed with the big MRF volume was really extended a lot into the main airflow. So I would say that between the small cylinder setup, let's say, and the setup between the rim spokes, the difference should be neglectable in my opinion. But again, it also depends a bit on the car. How big are the rims, you know, the volume of the rim spokes, how much work is done by the rims. It really depends also on the case. So I would say we have reached the hour here. I have a couple of more questions here. I would say, as I said at the beginning, gentlemen, please feel free to forward your questions to your dedicated support engineer. Refer to this broadcast, and we are really happy to follow up on that.
Peter, this is Scott. One question before we leave here that I thought would be useful. There was a question up on in the chat talking about the usefulness and accuracy improvements, performance improvements of using AMR, the automated mesh refinement, on external aerodynamics such as this. Can you comment very quickly on that?
Sure. To be totally honest, for steady state simulations with the new automatic CFL, we're able to couple with, to converge within, I would say, maybe 500 or 600 iterations. So that's really, really fast. So for steady state, I need a bit more testing, to be honest, on my side, but I don't see a big benefit here. AMR, I would consider AMR as really a game changer for water management applications. And you know, water management, for example, side window soiling and so on, it's also an aerodynamics challenge, problem at the end of the day. And for example, when you want to resolve droplets, you know, stripping from the side mirror, then AMR, I would consider AMR as a game changer there. But for the pure steady state aerodynamics, maybe even for the unsteady aerodynamics, I don't consider it as a game changer, like for the water management applications. I hope that answers the question quickly. Okay, I think that's it. Again, thanks a lot for joining, and take care. Bye-bye.